Earlier. Oh well. All right. No, I desperately. We have all this theory, and then we have concrete stuff that has to follow the theory. This is technically what all of the samples should come out to have a standard deviation of. We got 4 because we got 25 out of billions and billions and billions of possibilities. So I can live with that. It's gotten closer. It was this. We got to 4, and if I got all the samples, it would get down to 2.143. Now, the real mean is 80.054, blah, blah, blah. So theoretically, if I take a sample of 31, what's the probability that the sample mean would be greater than 81? Let's calculate this together. And then we can go actually concretely see how many did. Obviously, I couldn't have done this ahead of time. I have no idea right now how good this is going to bear out. But let's just try it. So theoretically, what percentage of people should have gotten a mean higher than 81? That's what this means. If you do it, if I have a bunch of people do it, this is going to tell me what percentage of those people should have gotten greater than 81. So how do I do this? What goes right in the middle? 80.05433. I like it. Then I make my z-score. 81 minus 80 point, get out of there, 05433 divided by the new standard deviation. Right? So I want to know the probability that a group of 31 has a mean greater than 81. I've got to use the new standard deviation. Somebody help me out a little bit. 0.48. Does that sound? No, it's the other way, 0.46. I don't know what the hell I'm talking about. Somebody help me. Oh, okay. I can live with that. I was pretty close. And then if I look that up, what area do I get? 0.44. I get an area of, oh, I love it, 67. That takes kind of some ass. So this will be 0.67, so I expect about 33%. That's kind of beautiful. I think, right? All right, let me stop. Does this work feel familiar? I know I'm doing it in a very different context. But it's the same as any problem. I've got a population. I've picked a sample of 31. I could talk about theoretically what percentage should be greater than 81, about a third. That's kind of a beautiful number to come up with. I didn't do this on purpose. Hopefully, obviously. So how many people are above 81? Let's see. This one's above 81. Oh, this one's above 81. This one. This one. Oh, shit, more than I thought. I think all of you guys were naturally drawn to the higher grades, maybe. This one and these two. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 out of, what was it, 25? It's like 48%. And what it should be 33%. Oh well. So I would predict about a little more than 8. 1/3 of 25 is like 8. And we got 12 people that got above that. Okay, man. So again, this is the beauty of statistics. Would it have been impossible? Would it have been totally impossible for every single person to get above 81 in this classroom? No. But it would be remarkably unlikely. And this is why people don't understand and don't like statistics. Theoretically, there should be 33% of the people. We got, what did we get? 48%. Which is still in that direction. But why is it different? Because every group would be different. This is just not really an average, because you can't really average percentages, but this is sort of like a long run thing. If I got another group of people and we have a percentage, and eventually it would become 33% in the long run. If I did this over and over and over again. Okay, maybe. That's the hardest thing about any math course is keeping in mind the theory versus the concrete reality. And statistics is really hard because it just makes predictions. And that's why I love my shirt today. Anytime you see statistics being used correctly, there's always got to be some mention of we're 95% confident that this is right. There's a 5% chance we're wrong. Does that mean that we don't know math? No, it means that that's frickin' life. That's why I love statistics. It's so real to life. In algebra, that thing is 7 feet long. No question, right? And then I'm like, in statistics, you're like 7 feet, give or take. I don't know. Maybe. Which is life. All right, sorry. Let's see. Let me try to take a picture of this before I want to do more with this shit later this semester. Let me take a couple pictures. Let's see if I can eventually see what that says. You guys keep track of your work for this. It's going to come back at us. Okay. So let's do a couple of review problems from central limit theorem stuff. Just to remember what the hell that is. So this is stuff from chapter 7. That's a lot of words for me. Shit. So before we get really specific with that number that we all know, this is really the beginning of central limit theorem. As sample size grows, the distribution of all sample means of that size becomes more normal. And to be honest, as I lose my voice, you're all like, yay, stop. And to be honest, good Lord. What was I going to say? Oh, what we did was we threw into a supercomputer we told it to create as many distributions as it could think of. And around size 30, when you got to sample size of 30 or more than 30, almost no matter what it started off looking as. It could have been disgusting as all hell. We did that one where it was numbers in a hat, remember? And it started off uniform. So it started off nice. So after just picking a sample of size 2, it became pretty normal. But it doesn't have to start off looking nice at all. It could start off looking blah, blah, blah. But for almost every possible sample, this goes on to say, if the sample size, this does say, before even talking about sample size, the new mean is the old mean, and the new standard deviation is the old one divided by square root of n. But then it says, if n greater than 30, distribution of sample means is normal enough. You're going to have to retire. We'll do that. That's the magic thing. So if I don't tell you that it's normal in the problem, and I'm asking you to create probabilities, to come up with probabilities, I must have taken a sample greater than 30 somewhere. So either I've got to say it is normal, period, and then how big of a sample is okay? 1. Because it's already freaking normal. So if I take a sample of 4, no problem. If I don't say it's normal, the sample size has got to be greater than 30 to be certain that I'm dealing with something normal enough. Normal enough for what? To use a chart to get all the answers. Maybe. So let's try a concrete example. This is all just a deep dive into theory. Not even really that deep, but deep enough. So here, let's try a problem. Oh, jeez. Are you working? Yeah. Let's see. Let's see. Winnings from bets on a basketball game are normally distributed with a mean of, let's say this is some small bar, so there's not a lot of, let's see, mean of $300 and a standard deviation of $71, just to make up some shit. Anybody watching any college basketball? I kind of am kicking myself in the ass. I was thinking about doing this semester, and I don't really pay attention to it, to be honest. Sorry if you do really big time. But obviously, as a stats teacher, I love the whole bracketology stuff. You guys create your brackets, right? And yeah, March Madness. And did you hear, like 3 or something years ago, there was, I can't remember the name of the group, but they were going to give $1 million to whoever correctly predicted before it all started what the Final Four was going to be and who would win. So you had to get everything correct, all the teams right. And the probability of that happening was so low, their expected value was good enough to go with. It was really great PR, and they pretty much knew they weren't going to pay anybody. You guys kind of with me? So anyway, if I would have been with it, I would have printed out brackets for everybody and said, pick the winners in each thing. Even if you don't know shit about basketball, very often those people do better than the people that do. Because anyway, yes?
I think that was a year that like 99.99% of people lost in like the first game because of like...
Yeah, that was when there were a bunch of lower seeds just kicking ass in the beginning. Okay. Because that's what'll happen, right? Anyway, if you don't know anything about college basketball or brackets or whatever, I'm sorry. I'll stop talking about it. So let's say this, and if I take a sample of 14 people, why is this a problem I still will be able to do? Why will I eventually be able to get probabilities for this problem? I've only got 14 people. It's normal. I already told you it's normal. I love it. Kick ass. If that wasn't there, this would have to be greater than 30. Or else you couldn't do shit. I'm never going to do that to you. That would be so evil to give you a problem that you would waste time on unless you noticed there's a little tricky, and that would be so... People always worry about that. But basically, every problem I give you should be doable. You're not going to waste time if you do it. Don't think, oh, this is the trick one. I don't have to do shit here. No, I'm never going to do that. You guys semi with me? It's sort of like when you start to learn the factor and every other answer is prime, you're probably wrong. You remember that? Get a little too excited. It's got to be prime. No. So here. What's the probability that sample mean from the 14 people is, where am I at? Is greater than $320? So what's the very, very, very first thing you should do? And why? There's two kind of answers I would accept here, sort of, but yeah, I would take any words uttered at this moment. Yeah.
Sample standard deviation.
Standard deviation. Now be careful, it's not... I'm never going to make a sample standard deviation out of this. I want to really be careful. Even if I give you S, you still have to do what we're about to do. It's not population versus sample, and I'm not just coming down on you because everybody has that thought in their head. That standard deviation works for what? What does this standard deviation work for? What does it tell you the spread of? Individuals. And what do I need? Standard deviation for groups of 14. Even if this was an S, I would still have to divide it by the square root of 14, because S is for individuals, S sub x bar would be for groups of size 14. I love you guys. I love you guys so much. So you're not taking sigma and making S out of it. You're not making a sample. No, you're making the standard deviation for all sample means, not for all individuals. So the very, very, very first thing I should do, I would have accepted draw a picture, but very first thing I should do is take the old standard deviation divided by square root of n. And then whatever the hell that is. It's like 18 point? 98? 980? 975. Yeah. Let me see. I just gotta find. I just gotta make it out there to get some more. Is that cool?
Yes.
I'll write bigger too. I always forget. All right. So that's the spread for the problem I'm given. This spread, I needed it, but I can't use it directly because I'm talking about groups of size 14. Now I do all the normal shit. Right? And when I say normal shit, the standard z-score problem should be easy as all hell by this point. Make a z-score, look it up in the table. Is it the right area? Do 1 minus sometimes, subtract, whatever. Bam! So now I can just do that. What goes in the middle? 300. 320 is up here somewhere. Greater than, so I want this area. And then what do I do? What do I do now? How do I get that probability? What's the middle step? I want to get the answer from the z-score chart, so I better make a z-score so I can use that chart. I love you guys. So my score minus the mean divided by the spread. Why does that answer make sense? Because one step is 18.9. One step up almost gets me to 320, doesn't it? So don't lose the sight that a formula isn't magic in itself. It just captures a process that we would do anyway. We actually did this process before we knew that formula. I don't know if you guys remember that. Okay, and now what do I do? That's obviously not the answer, because I told myself it's a z-score. So now I look that bad boy up. What's the area below? 8541? 8531. And so the actual answer is going to be 1 minus that. Okay, so here's the problem for you to try. Same stuff. This is part A. Part B is take a sample of, what you got, Jeff? Let's say take a sample of 98 people. Now find the probability that X bar is greater than 320. Are you with me? So now the question is, take a sample of 98 people instead of 14. What's the probability that the average winnings is more than 320? Should that be higher or lower than this? Should there be more people, more groups of size 98 weigh the shit out here, or less? Less. I kind of led you on with my tone, but oh well. If I take 98 freaking people, what should their average be? It should be close to 300. I got 98 people. Shit. Should be really close to the actual average. Should be very few way out above 320. Let's see if that comes out in the work. While you're doing that, I'm going to give out the practice test.
Yeah.
Was there already like almost 9? Damn! Alright. Yeah, I got a meeting at 9. Sorry, I wasn't like trying to keep you overtime. Just let me know. Obviously, I didn't even look.
Yeah.
We'll worry about that problem. Somebody remind me about that problem next time. You guys got the practice test, so I'll have the answer key on Wednesday. I'll see you then. Oh, please don't forget your IDs and such. Yeah, like it says on the homework sheet, it's still on Monday, the 8th. Yeah, let's see. There it is. Find out fast. Thank you.